So thank you for inviting me to give this talk. So I'm going to be talking about the role of CO2 in mobilising metals through the lithosphere. And this is essentially the work I carried out as part of my PhD. And I just want to highlight everyone that has been involved in various aspects of this work. So as mentioned, this is research that's come about my PhD, and the focus of this talk is going to be mainly a paper that I published in that first publication from the PhD a few years ago, but this is the first time where I'm able to actually present this to a wider audience. So I've only so far presented to CET, so apologies for those from Western Australia in the audience. But the kind of outline of this talk is, so initially is where I started looking at carbonate and sulfide. And this was from my PhD focus on the Manali nickel deposit, where we've got the initial carbonate sulfide recognition. And then the main bulk of the talk will be looking at other case studies where we're seeing carbonate and sulfide. And a little spoiler alert that these are more alkaline affinity salt magmatic systems that are in place into the lower mid-crust, and then applying these to the magmatic sulfide models that we use and apply today, and then looking up into the upper crustal systems and implications for this. So first off, looking at the Manali deposit. So this is where I initially came to start looking at the carbonate sulfide association. And for those that don't know, just a quick background is that the Manali nickel deposit is a relatively small mafic, ultramafic complex, placed in the Neoproterozoic, residing within the Zambezi belt. So this is between the Congo craton and the Kalahari craton. And it's relatively small, comprising gabbros, olivine gabbros, and orthopyroxene poor ultramafic rocks, including pyroxenite, whorlites, and dunites. And in terms of the sulfide and the actual deposit itself, it represents on a broad scale a relatively conduit style magmatic sulfide deposit. So we've got the accumulation of massive sulfide, which is predominantly sulfide rich, and here representing the fractionated body, but it's associated with the ultramafic rocks. And I have done, at the last nickel symposium, I presented on the actual fractionated component of this deposit, and there's a paper out if you're interested in that. But for the relevance of this talk is that one of the unusual aspects of Manali is that it's host to abundant carbonate. Carbonate associated with sulfide. So we've got carbonate within the ultramafic rocks and within the main sulfide ore body. So in the top images, we've got interstitial calcites that's residing within the sulfide. And here's just a CT scan to show that network of calcite within this sulfide ore. But the bulk of the ore body is we've got dolomites that's associated with sulfide, and then the bottom images are showcasing some of these sulfide blebs that show magmatic textures hosted within dolomites. So this has led to a number of theories on the component of carbonate here. So it has been suggested that this is potentially mantle derived, and the system represents a more ultramafic end member of a carbonatite complex. So kind of one way to look into this was doing carbon oxygen isotopes of the carbonate. Although it's just important to note that Manali is situated almost completely within a unit of marble, within relatively quite silicic rich sediments. And this marble has quite high, heavy isotopic carbonate signatures, so we've shown in the blue up in the right-hand corner. However, the bulk of the ore kind of sits in this intermediate range. So this is the carbonates with the sulfides. And this is kind of suggesting that we've actually got the interaction of carbonate within the sulfides from the country rock rather than it being mantle derived. So this is just highlighting how I got into the carbonate and sulfide association. So although it's not particularly the mantle component, it is important for the sulfide orogenesis at Manali. And this is mentioned within the paper that's out in Economic Geology, and there should be one soon in Ore Geology Reviews. But then just thinking kind of broadly is that when I was looking at this sulfide and carbonate is whether we actually see carbonate with sulfide in other magmatic sulfide systems. And normally where we've done a hunt looking for primary looking carbonates, and it's not really widely reported carbonate within magmatic sulfide complexes because it's typically considered to be either a late stage or a hydrothermal process. But here's just showcasing some of the examples that was mentioned more in the paper, but where we've got from the mantle up into the crust. So we've got some mantle xenoliths samples, some from the lower crust examples and up into the mid crust. And essentially what this did involve was that every time we've seen a sulfide deposit, I now go up and down acid to see where we're seeing carbonates with sulfides. And we actually do see, it's very common to actually see what we've seen in the video, where if they've got carbonate, not within the actual rock itself, with sulfide. And we see these in a range of different magmatic deposit styles. So just starting off from the mantle as our case study, the mantle is considered one of a source of not just metals, but also melts and volatiles. And carbon in the mantle is a big reservoir of carbon in the form of metal carbides, diamonds, graphite. And here we've got showcasing some carbonate examples. And the association of sulfide and carbonate is widely reported. So you've got the xenoliths from Victoria in Southeast Australia, as well as sulfide and carbonate from the Loch Rag intrusions reported by Hannah Hughes in Scotland. But here I'm just showcasing 3 case studies where we see different textural styles of this carbonate and sulfide. So the first is in Patagonia. So this is samples provided by Santiago Tessara, which is sampled beneath the Auriferous province in Argentina. So what we see here is that we've got sulfide and carbonate together in interstitial spaces of the silicate phases. And in addition to this, we see volatiles in the form of apatite, as well as inclusions of palladium tellurides and minerite. So this is palladium telluride is the theme that we'll follow through. So another example is the Marid xenoliths from Bullfontein. So these are quite alkaline and volatile rich xenolith samples. And in these images, we see that we've got sulfide, metals, and carbonates forming these pools in these xenoliths. And then the last example is Felture carbonatite. So these are xenoliths, actually the bottom image, sampled, bottom xenolith, which are sampled from the tufts of this carbonatite. And again, we're seeing these rounded calcites, sulfides, and even barite phases. And these have all been used to suggest that we've got a metasomatically modified mantle. And then looking into our more crustal example, so the first locality visited was the Urea zone, which is one of these natural laboratories, and it's a perfect case study as we've actually got a cross section through the lithosphere from the mantle up into the crust. But what we were interested in was these lower crustal ultramafic pipes. So these are quite hydrous and carbonated and mildly alkaline that intruded into the base of the crust. And these are host to sulfide mineralization, was actually during the war, during the First World War. But it's the sulfides that was of interest here. So this was the first locality in that there was reports that we had carbonate with sulfide. And what we can see is that we've got these centimeter-sized sulfide blebs, primarily comprising pyrrhotite, pentlandite, and chalcopyrite. And here we've got in calcite in the blue that forms these rims around the sulfide. So we're seeing these quite remarkable textures. And this is just exemplified in these bottom images, where again, we're seeing these carbonate forming the rims along the sulfide. And in addition to this, we've got inclusions within the sulfide itself, as well as palladium nickel tellurides. And just important to note that these sulfides show mantle-like self-isotope compositions. And then moving up into the mid-crust, one of the examples showcasing is the Shrungarb intrusion in Scotland. So this is a alkaline diorite apenite intrusion in place around 400 million years ago in Scotland. So this is just a geological map where we've got the diorite in red, but what we're interested in these apenites that are on the margins of the diorite, they're actually the host to the sulfides. So again, we were seeing these sulfide blebs here. They're more centimeter size, comprising a more copper-rich assemblage where we've got chalcopyrite, pyrite, some pyrrhotite, but nickel in form of nickel tellurides, and associated with gold. So what we see is that we've got these sulfide blebs and we've got carbonate, again, along the rims of the sulfide. And in the middle, if you truly believe, there's a little unicorn. And in the right images, we've got calcite that's not completely with the sulfide and on a different form. So it's not as pristine as what we're seeing in the Urea zone. And then another example in the mid-crust is the mordor alkaline igneous complex. So this was in place around 1.1 billion years ago in the Northern Territories of Australia. And it's got its name from this image where it's got this quite remarkable free-ridged topography that's shaped like the Mordor in Tolkien books. And if we look at the geological map, what we can see is that we've got this zoned alkaline cyanide ultramafic intrusion, where we've got the ultramafics in purple and these mafic strontianites, which are essentially mafic cyanites, surrounded by more traditional cyanites with this, interestingly, this calcite barite plug. So there's two types of mineralization at Mordor. The first being that we've got these PG reef style, which is not the focus of this talk and has been reported by Steve Barnes. So there's a paper on that where it's hosted within the ultramafic parts of the system. But what we're interested in is sulfides, and this occurs within mafic cyanites along the margins of the whole intrusion, where we've got enrichments of platinum, palladium, gold, and copper. So again, just showcasing some of these sulfides. So we've got these sulfides similar to what we see at Strongard, where it's pyrrhotite and chalcopyrite, pyrite, with nickel in the form of millerite and nickel tellurides. But what we're interested in is that, again, we was running the carbonate up and down the drill core, and it was only with sulfides where we was association with the acid. And looking closely at the sulfides, we see that we've got these inclusions of calcite hosted within the sulfide itself. So kind of a summary of the different case studies we have is that we've seen a presence of blebby sulfides that have an association with carbonate, where the lower crustal intrusions have a much more pristine texture and a bit more dissociated up into the mid-crust. And these are also associated with more alkaline rich host rocks, and typically this mineralization occurs along the margins of these intrusions. But again, we're seeing this assemblage of this nickel copper assemblage with nickel palladium tellurides. So just coming back to the carbon isotope, so unlike Manali, which showed a more crustal contamination signature for the carbonates, what we see in these lower crustal intrusions that we see much more mantle-like signatures for the carbonate alongside the sulfide-derived mantle-derived sulfides. So in terms of how this fits into our current understanding of how to form magmatic sulfide deposits, so typically in order to liberate the maximum amount of metals, we really do need high degrees of partial melting. And this is typically formed, this model is using a more dry sulfide saturated melts. So as mentioned, it seems that we've got a dry peridotite source where the metals are predominantly coming from either the sulfide or nickel from the olivine. So this doesn't really take into account whether we've got volatile rich assemblages or even incongruent melting. So in this case, where we've got incongruent melting of sulfides, we would liberate copper and tellurium at much lower degree partial meltings. And this is what we see in these alkaline systems where we've got low degree partial melts that are more copper, tellurium, and even gold dominant. So another problem in forming a typical magmatic sulfide. So we've got the mantle as a source for most of the metals. However, in these models, we do assume that we need high degrees of partial melting to actually get the sulfides and the metals. However, these we rarely see enough melting to actually completely exhaust the sulfides and the metals. So we're actually retaining a lot of the sulfide and metals in the mantle. And this is a problem because, as mentioned, sulfide's dense, so it's not easily transported. And I'm just going to use the diagram from Nesher, just highlighting these various components for actually transporting magmatic sulfide. So in the yellow represents a more centimetre-sized sulfide bleb. And in order to actually transport the sulfides, we really even need to decrease the buoyancy of the sulfide itself, increase the velocity, or even decrease the size. So technically, it shouldn't be able to make it at the mantle. So typical models assume that we've got more chemical interactions actually liberating the metals, whereas in the physical process, we still shouldn't be able to make it out the mantle in this situation. However, so we see an association of carbon and sulfide together. So essentially, the shown affinity could potentially form compound droplets. So at this pressure and depth that we look at in the lower mantle, the carbon would be present as a CO2 supercritical fluid. So this is quite critical. So if we've got our sulfide droplet, if we form a compound droplet, we're essentially decreasing the buoyancy of not just sulfide compound, but essentially the knot itself. So this allows potentially this transition of this upward transport from the mantle into the crust. And this has been quite a topical recently, and two of the keynotes have highlighted this process of this bubble enhanced transport. So these really focus on the upper crust. So we've got Louisa presented her bubbles in a wine glass, and so this is focused on the upper crust, and this has essentially been associated with sulfide, with more hydrous fluids, and then the bottom image just highlight how this has been proposed for the flotation of magnetite in iron oxide apatite deposits such as Elaco. But what's quite critical is that it has been suggested that these dynamics of compound droplets are not pressure sensitive. So essentially what we're seeing in the upper crust could be applicable to the lower crust, in which our case studies are. So one of our big issues is that we actually need carbonate in the mantle to be able to form these compound droplets and transport the sulfides. So one way to do this is actually either decreasing the amount of partial melting or increasing the amount of CO2 initially, such as from an enriched source. So there are a number of ways that we can actually enrich the amount of carbonate in the mantle. And one way of doing this is by subduction. So subduction is known to actually enrich the mantle and even the mantle wedge in modifying these components. And what's been shown by a number of researchers is that this subduction can not only increase the amount of carbon in the form of serpentinized basalts or even carbonate units themselves, but also tellurium and sulfur, gold, PGs, and copper, which is kind of our characteristic signature for this association. So another way that we can actually increase the amount of CO2 in the mantle is by interaction of these low degree partial melting with the mantle itself. So silica contamination actually can trigger CO2 and sulfide saturation. And another way to do this is even for welatization, which actually causes increase of CO2 in the mantle. So then this goes up into the crust, where into the lower crust, we've got the snapshot of our model in process, such as the Ivrea zone, and then up into the mid crust, where this association starts to separate. So, and this is due to different properties of the solubility in carbonates and sulfide, which are more pressure sensitive. What happens when we get to the upper crust? So this is where things start to separate, and there's two potential situations. So we've either got that the carbon and CO2 and sulfide start to separate, as mentioned, or we've even got resorption of the sulfide itself, and then the metals being liberated back into the melt and able to be further utilized. However, the preservation potential for this is quite low. And I just want to highlight a talk by Maria Sherdantseva, who did highlight this association in the mid to upper crust. To this association mid to upper crust, where she links that potentially some metals could be going with the CO2 vapor. So just the kind of end members to this. So could this be forming other alkalic epithermal porphyry systems? So the CO2 within this system should actually remain within the distal footprint. So although it's being separated, it's still within the whole system. So these are just some examples of where we're seeing these copper, tellurium, and even PGE associations within these epithermal and porphyry systems. So here we've got examples such as Cripple Creek, Scouries, and even Emperor and Tuvatu gold tellurium epithermal deposit. And in addition to this, it has, not only is it potential links to epithermal and porphyries, but it has been noted that even gold and carbonate show a strong association, together. So, and whether we actually see these tellurium-rich end members such as Kalgoorlie representing one of these end members. So kind of to summarize into our working model and coming back to this, coming back to the rocket. So essentially what we're proposing is that the sulfide represents the main rockets. This is the sulfide and the metals, whereas it's the carbon as a supercritical CO2 fluid that actually is represented as jet boosters. So this helps that energy needed to transport these from the mantle into the crust. But by the time we get to the upper crust, the association has separated. So with this working model, so far it has been focused on these more low degree partial melts. And this is because this is where we're most likely to be both sulfide saturated and CO2 saturated. So the questions arise whether this could be applicable to more volatile rich melts, ones that are more high degree partial melting, and whether this process could actually prime magmatic sulfide deposits for potentially later cannibalization. So kind of the three main implications for this research and kind of the summary of this slide is that whether we've got the potential, so far, the case studies we've shown are quite relatively small sulfide deposits. So it's whether we can actually form larger and even economic deposits, and whether these mechanisms can actually, whether we can actually concentrate the sulfide up in the crust. So an example of this would be the Curacao Valley, where we actually see sulfides and carbonates within the same system. And then, as mentioned before, whether this could be actually a process that's an early part of most magmatic sulfide deposits in terms of early stage melting and mobilization of metals to be later consumed. And then the last point is that although we've been focusing on the lower crust, this carbonate sulfide association can occur within all crustal depths. And I know a lot of the work coming from the CSR at the moment is showcasing where we potentially got carbonate associated with sulfides in more the mid and lower crust, such as Nova and Norilsk. So that's kind of a summary of the paper for this talk. So thank you for listening. And if you've got any questions.